Look around you. Everything you see, from the chair you're sitting on to the air you breathe, is made up of tiny particles called atoms. Atoms are the fundamental building blocks of matter. They are incredibly small, far too tiny to see with the naked eye. Yet these minuscule units hold the key to understanding the vast and complex universe we live in. Atoms are like miniature Lego bricks, combining and interacting to create the incredible diversity of materials we encounter every day. Imagine a world without atoms. No stars, no planets, no life itself. Atoms are the foundation upon which the grand symphony of the cosmos is built. But what exactly are atoms made of? For centuries, this question remained a mystery, pondered by philosophers and scientists alike. Let's journey back in time to explore the fascinating evolution of our understanding of these fundamental particles. The idea of atoms has been around for a surprisingly long time. In ancient Greece, around 400 BC, a philosopher named Democritus proposed the existence of tiny, indivisible particles, called atomos, meaning uncuttable or indivisible. Democritus believed that these atoms were the smallest possible units of matter, and that everything in the universe was made up of different combinations of these particles. He imagined atoms as being eternal and unchanging, constantly moving and colliding in the void. While Democritus's ideas were groundbreaking for his time, they were largely based on philosophical reasoning rather than experimental evidence. His theory faced opposition from other influential thinkers like Aristotle, who favored a model of the universe composed of four elements: earth, air, fire, and water. Despite the lack of scientific validation, Democritus's concept of atoms laid the groundwork for future generations of scientists to explore the nature of matter. It would be over 2,000 years before the idea of atoms would be revisited and refined with the dawn of modern science. Fast forward to the 19th century, a time of great scientific discoveries. In 1808, an English chemist named John Dalton revived the atomic theory, propelling it into the realm of modern science. Dalton's atomic theory was based on experimental observations and laid the foundation for our current understanding of atoms. Dalton's theory can be summarized in a few key points. All matter is made up of tiny, indivisible particles called atoms. Atoms of the same element are identical in mass and properties. Atoms of different elements have different masses and properties. Atoms combine in simple whole number ratios to form chemical compounds. In chemical reactions, atoms are rearranged, combined, or separated, but never created or destroyed. Dalton's atomic theory was a major breakthrough in chemistry. It provided a simple and elegant explanation for the laws of chemical combination and laid the groundwork for the development of the periodic table of elements. Dalton's atomic theory was a triumph, but it wasn't the end of the story. As scientists delved deeper into the atom's mysteries, they discovered that it wasn't as indivisible as once thought. The late 19th and early 20th centuries witnessed a series of groundbreaking experiments that revealed the existence of even smaller particles within the atom, subatomic particles. In 1897, J.J. Thomson, a British physicist, discovered the electron through his experiments with cathode rays. He found that these rays were composed of negatively charged particles much smaller than atoms. Thomson proposed a model of the atom resembling a plum pudding, with negatively charged electrons embedded in a positively charged sphere. Then came Ernest Rutherford, a New Zealand-born physicist, who in 1909 conducted his famous gold foil experiment. By firing alpha particles, positively charged particles, at a thin gold foil, Rutherford expected most of the particles to pass straight through, based on the plum pudding model. To his surprise, a small fraction of the alpha particles were deflected at large angles, some even bouncing back towards the source. Section 5. Rutherford's atom, a peek inside. Rutherford's experiment revolutionized our understanding of the atom. His results led him to propose a new model in 1911, the nuclear model. According to this model, the atom consists of a tiny, dense, positively charged nucleus at the center where most of the atom's mass is concentrated. The negatively charged electrons orbit the nucleus at a distance, much like planets revolving around the sun. Rutherford's model was a major departure from Thomson's plum pudding model. It explained the deflection of alpha particles in the gold foil experiment as a result of the strong electrostatic repulsion between the positively charged alpha particles and the positively charged nucleus. However, Rutherford's model wasn't without its limitations. It couldn't explain why the orbiting electrons didn't lose energy and spiral into the nucleus, as classical physics would predict. Moreover, it couldn't account for the specific wavelengths of light emitted and absorbed by atoms known as atomic spectra. To Section 6, Bohr's refinement electrons in specific orbits. In 1913, Danish physicist Niels Bohr stepped in to address the shortcomings of Rutherford's model. Bohr proposed that electrons don't just orbit the nucleus randomly. Instead, they occupy specific quantized energy levels or shells. These shells are like steps on a ladder, with each step representing a specific energy level. According to Bohr's model, electrons can only exist in these specific energy levels, not in between. When an electron absorbs energy, it jumps to a higher energy level, further away from the nucleus. Conversely, when an electron loses energy, it falls back to a lower energy level, closer to the nucleus. This process of electrons jumping between energy levels explains the specific wavelengths of light emitted and absorbed by atoms. When an electron falls back to a lower energy level, it releases energy in the form of a photon, a particle of light, with a specific wavelength corresponding to the energy difference between the two levels. Bohr's model was a significant improvement over Rutherford's model. It explained both the stability of atoms and the observed atomic spectra. However, it was still incomplete and couldn't fully explain the behavior of electrons in more complex atoms. Section 7. The quantum leap Schrödinger's model. The quest to unravel the atom's mysteries culminated in the development of quantum mechanics in the 1920s. Austrian physicist Erwin Schrödinger revolutionized our understanding of the atom with his wave equation, which provided a mathematical description of the behavior of electrons. Schrödinger's model, developed in 1926, abandoned the idea of electrons orbiting the nucleus in fixed paths like planets. Instead, it described electrons as wave particles existing in a cloud of probability around the nucleus. This cloud, called an orbital, represents the region of space where an electron is most likely to be found. In Schrödinger's model, electrons don't have definite positions or trajectories. Instead, their behavior is governed by probability waves, which determine the likelihood of finding an electron at a particular point in space. The model accurately predicted the energy levels and spectral lines of atoms, even for complex atoms that Bohr's model couldn't fully explain. Schrödinger's quantum mechanical model is the most accurate and comprehensive model of the atom we have today. It forms the basis for our understanding of chemical bonding, the behavior of materials, and countless other phenomena in the realm of chemistry and physics. Section 8. Electrons, protons, neutrons, the key players. So far, we've mainly focused on electrons and their journey in unraveling the atom's structure. But what about the other inhabitants of the atomic world, protons and neutrons? These subatomic particles reside in the atom's nucleus and play a crucial role in determining its properties. Protons, discovered by Ernest Rutherford in 1917, are positively charged particles located in the nucleus. They carry a charge equal in magnitude but opposite in sign to that of electrons. The number of protons in an atom's nucleus, called the atomic number, defines the element to which the atom belongs. Neutrons, discovered by James Chadwick in 1932, are neutral particles also located in the nucleus. They have a mass slightly greater than that of protons. The number of neutrons in an atom's nucleus can vary, giving rise to isotopes, which are atoms of the same element with the same atomic number but different numbers of neutrons. The nucleus, composed of protons and neutrons, accounts for almost all of the atom's mass. The strong nuclear force binds these particles together, overcoming the electrostatic repulsion between the positively charged protons. Section 9. Isotopes, ions and applications, the power of atoms. The discovery of subatomic particles and the development of quantum mechanics revolutionized our understanding of atoms and their behavior. This knowledge has paved the way for countless technological advancements and applications that have transformed our world. Isotopes, atoms of the same element with different numbers of neutrons, have unique properties that make them valuable tools in various fields. For instance, carbon-14, a radioactive isotope of carbon, is used in archaeology for carbon dating, determining the age of ancient artifacts. Ions, atoms that have gained or lost electrons, are another essential concept in chemistry. They play a crucial role in chemical reactions, electrical conductivity, and biological processes. For example, sodium ions, Na+, and chloride ions, Cl, are essential electrolytes in our bodies, regulating fluid balance and nerve function. The applications of our understanding of atoms are far-reaching and diverse, from nuclear energy and medical imaging to materials science and nanotechnology. Nuclear power plants harness the energy released from nuclear reactions, providing a significant portion of the world's electricity. Medical imaging techniques like X-rays and MRI rely on our understanding of how atoms interact with electromagnetic radiation, enabling us to diagnose and treat diseases. The journey into the atom's heart has been a long and fascinating one, marked by scientific curiosity, ingenuity, and collaboration. From ancient philosophical musings to sophisticated quantum mechanical models, our understanding of these fundamental building blocks has come a long way. As we delve deeper into the subatomic realm, we continue to unlock new secrets and possibilities, shaping the future of science and technology.